it possible?
It's Wednesday.
Okay, good.
First I know. I know that I know.
Okay, so everybody got my email yesterday about taking that one problem, the last one, off the problem set and putting it onto the extra credit problem set. So now you have 4 problems due tomorrow instead of 5. Okay? The extra credit problem set, I just went ahead and posted it on Blackboard instead of printing it out. Okay? And we said that it would be due at the latest at the time of the final. Okay? Which again is, well, now it's a week from Monday. So I'll talk more about it on Tuesday's class. We talked a little bit about it. I'll give you a little bit more detail about it on Tuesday's class. Okay? Okay, any questions for me about anything? Yes?
Do we still get the one quiz dropped?
Mm-hmm. Yep. I said I would drop the lowest quiz, and I thought I said I'd drop the lowest problem set.
Okay.
Didn't I?
Yes.
Yeah? Okay. And when I say the quizzes were all worth the same number of points, so that would be easy. It's just the lowest one. Problem set, it'll be the lowest percentage that you earned possible. I'll drop that. Okay. Any other questions? Okay. Let's get the brain working, thinking about the material we've been talking about on Tuesday. On Tuesday, we said we were going to start in Chapter 7 looking at systems that could not be treated classically, or even what some books call semi-classically. We were going to look at what were fully quantum mechanical systems. And that's, of course, a little bit of a vague phrase. Well, what do you mean by fully quantum mechanical? Or what's the condition for treating a system fully quantum mechanically? And the condition we had involved this quantity called the quantum volume for a given system. And remember how we calculated that? We calculate the quantum volume for a system by taking Planck's constant. That's how you know it's a quantum expression. If Planck's constant's in it, you know it's not classical. Okay? Over the square root of 2 times pi times the mass of any of the particles that you have times Boltzmann's constant times the temperature, all that gets cubed, because it's the quantum volume. Okay? This has to be, if we're going to do a fully quantum mechanical approach, this has to be of about the size or equal to the volume per particle that's available to the particles in the system. So this is the total volume that's available to the system, and this is the total number of particles. Okay? So when the quantum volume gets big enough to be comparable to the volume available per particle, what that really means is that the particles' wave functions all start to overlap with each other. And you cannot treat the system classically anymore. So when this is true, right, it's not or no semi-classical analysis allowed. And so when you're doing a fully quantum mechanical analysis, what is happening? What are you worried about? And you are worried about the possibility, when you're in a situation like that, where you have multiple particles trying to occupy the same quantum state at the same time. That's what the problem is. You have multiple particles trying to occupy the same quantum state at the same time. And when that is happening, it turns out you have to allow for the fact that in nature there are 2 categories of particles. Okay? And Anybody remember the names of these categories? Fermions and bosons. And they are distinguished, these categories of particles, by how they deal with multiple particles trying to occupy the same quantum state at the same time. Namely, fermions absolutely forbid more than one particle in a quantum state at the same time. Okay? Whereas bosons, they're fine with it. They allow more than one particle in the same quantum state at the same time. Okay? And so you have to worry about, are your particles fermions or bosons? Now, I mentioned briefly where this behavior ultimately comes from. The fermionic behavior of not allowing more than one particle in the same quantum state at the same time versus the bosonic behavior of being fine with having more than one particle in the same quantum state at the same time. Where does that come from? The answer is it comes from quantum mechanics. And it comes from the properties of solutions to Schrodinger's equation. All right? And if you have multiple identical particles and they're fermions, then it turns out the wave function for a multi-particle system has to have a special property. That if you switch the labels on any two of the particles, the wave function has to pick up a negative sign. Now, where does that come from? Well, that's a little bit more advanced quantum mechanics, but that's what fermions must have. Their wave functions must have that property. If you switch the label on any two of these identical fermions, the wave function itself picks up a minus sign. And then you can show that if your wave function has that property, that switching the labels on any two of the particles picks up a negative sign. Right? If your wave function has that property, then you can also show that by the virtue of having that property, if you try to have two particles in the same quantum state, that wave function vanishes. Which means there's no probability for two particles in the same quantum state. That's the Pauli exclusion principle. Okay? So it comes from that property of the wave function, that switching two labels picks up a minus sign. That's where the Pauli exclusion principle comes from. Bosons have the property in their wave function that if you switch any two labels, the wave function doesn't pick up a minus sign. It keeps the same sign. And then you discover that if you do switch two labels of your particles, the wave function doesn't vanish. Therefore, there is a probability that that can happen. So in a fully quantum mechanical analysis of a system, you're worried about multiple particles trying to occupy the same quantum state at the same time, and then you have to know, am I dealing with fermions or am I dealing with bosons? Okay? So we're going to start today with a little bit of practice dealing with fermions versus bosons and putting multiple particles in the same quantum state at the same time. Okay? So this, what I want to do is an example problem from your book that is kind of a cooked up problem, not really realistic in what you would do if you were doing research, but it's good practice getting used to dealing with bosons versus fermions. Okay? Versus thinking classically. So the scenario goes like this. We have a box, a container, in which each particle may occupy any of 10 single particle states. A single particle state is a solution to Schrodinger's equation for one particle. Okay? And a single particle state will be described by some set of quantum numbers. So we have 10 of these single particle states that are available when we have a particle in this box. Now normally you're going to have a lot more than 10. That's why it's a cooked up example. Let's assume that each of these states corresponds to zero energy, so they're all degenerate. Okay? And that all the particles in this problem are non-interacting. Wouldn't that be nice? If that were really, really true. Okay? But that's what we're going to assume. Let's warm up by first just calculating the canonical partition function. Canonical. Chapter 6. For this system, assuming there is only one particle in the box. This is the simplest scenario possible. Okay? So, okay, you can imagine some box. In this box, we're going to put a particle. There are 10 single particle states, 10 quantum states. They all have the same energy, 0. Okay? Calculate the canonical partition function. Well, this will clearly be a single particle partition function, so I'm going to label it Z sub 1. There's only one particle in this box. Okay? I'm not going to change any definition of anything. The canonical partition function is the sum over all the possible states. We'll use a label S. The Boltzmann factor, e to the minus beta times the energy of state S, right? So we're summing over, in this case, 10 microstates that all correspond to the same energy, the energy being 0. So of course, if the energy is 0 for each microstate, this Boltzmann factor just becomes a 1. So all I'm really doing is counting the number of microstates, which of course will be 10 in this case. So Z1 is 10. Can't get much simpler than that. Okay? So that's a warm-up. Now, B. Suppose we have 2 particles that are put into this box, and therefore must go into one of these 10 single particle states. Got to go into those. There aren't any others. But the particles are distinguishable for one reason or another. They're different species. Who knows why? But you can tell them apart. So that, for example, they're not both electrons then. Okay? Maybe one's a neutron and one's a proton. You can tell them apart. Okay? So, 2 particles, they are distinguishable. Calculate the canonical or partition function. Well, I'm going to start having to do counting now. The counting here was trivial in part A. So let's denote the single particle states that are available. I just need some way to keep track of them, to represent them. Let's denote them with boxes. So there'll be 10 boxes. 4, 5, 6, 7, 8, 9, 10. Okay? Those represent the states, the 10 states. And the particle species, I guess I'll use the word species here, will be denoted A and B, because A and B are symbols that are distinguishable from each other. Okay? And I am supposed to sum over all the possible states for this situation, the Boltzmann factor for each state. Okay? Well, a state corresponds to taking A and putting it in one box, i.e. putting in one of the 10 single particle states, and taking B and putting it into one of the boxes. Okay? And don't worry about, do I have to worry about the Pauli exclusion principle? That doesn't even come into play when the particles are distinguishable from each other. Okay? So you can put A, right? You just do the counting, right? We have 10 choices for A. 10 state choices for particle A. And quite separate from that, we have 10 state choices for particle B. Okay? So, how many... Now, and every time I put A or B into a state, the energy is 0, so the Boltzmann factor is still just 1. Okay? But how many states are there? Any thoughts? This is now going to be a system state. System state meaning you got to allocate A somewhere, and you got to allocate B somewhere. Once you've allocated A and B, you have a system state. How many are there?
What do we count in torques? 45 for each. So there would be 10 choose 2.
Well, how many choices do I have for A?
Yeah.
Okay. How many choices do I have for B? 10. How many do I have total?
20?
You added.
Oh, we multiply.
You multiply.
It's 100.
100. 100.
Because the sum of the partition function, not the sum, but the most.
It's the product. It's the product, right? You can think of this as the partition function for A alone times the partition function for B alone. Right? Because they don't interact with each other. And they're distinguishable. Right? That's how we did it in chapter 6. If there was a multi-particle system with distinguishable, non-interacting particles, just take the individual partition functions and multiply them together. Okay? So there will be 100 microstates available. Okay? That's if they're distinguishable. Okay? Just make a list if you want, but you'll find you can do 100 of them. Now, C. 2 particles in the box, 10 states. The particles are identical bosons. Okay? So now, we have 2 identical bosons. So now, we've got the 10 states. 6, 7, 8, 9, 10. And into those, I'm going to put 2 identical bosons. So I'm going to represent the bosons by dots. Those are the 2 bosons. 2 bosons, the boxes are states. A boson must go into one of the states, one of the boxes. Okay? The Boltzmann factor, the partition function will be the sum of the Boltzmann factors for all the possible states. That means all the possible ways I can put those 2 bosons into those 10 boxes. Okay? So it's counting again. But we've done this kind of counting before. Different context. Some time ago.
Chapter 2.
Chapter 2. Yes? Think about the Einstein solid, where we had some number of oscillators and some number of energy quanta that were to be divvied up amongst the oscillators. Yes? It's the same thing. Right? Okay? So, number of microstates is the same as the number of ways of distributing 2 identical objects into 10 containers, if you like. I'll put the word containers. Quotes. Containers mean states. Think back, blast from the past to the Einstein solid, okay, where we might ask about for the number of ways of distributing 2 energy quanta among 10 oscillators. And so it's a multiplicity basically, yes? The symbol we used, remember, was this, omega. So back to the Einstein solid, we have 10 oscillators and 2 energy quanta to distribute amongst them. How many ways to do it? Well, if you remember the formula, it's 10 plus 2 minus 1 factorial in the numerator, and 10 minus 1 factorial times 2 factorial in the denominator. So that's 11 factorial over 9 factorial times 2 factorial. That will simplify to 11 times 10 over 2, which is 11 times 5, which is 55. So apparently there are 55 ways to distribute these dots amongst these boxes. Now, just to make sure, I want all this to be no mystery. Let's actually convince ourselves that there are 55 ways to do it. Okay? Let's think about the counting ourselves. I want to think about this counting by categorizing these 55 microstates into 2 groups. Those microstates in which there is, in terms of occupancy of the 10 states, each of those 10 states has either 0 or 1 occupant, versus microstates where there's one of the states, one of the boxes, that has 2 bosons in it. Double occupancy. Okay? So first, what we'll call the single occupancy microstates. Let's count up all the ways we can put the bosons into the 10 boxes, putting no more than 1 in any given box. No more than 1 in any given box. Okay? Well, it's just a matter of thinking about it for yourself. For example, you could start by saying, okay, put 1 boson in box 1. By box 1, I mean the one on the left. Then, how many ways do I have available to me to distribute the second boson? There are 9 other boxes. Yes? So there are 9 ways to do that. Put 1 boson in the first box and 1 boson in one of the other boxes. Okay? So, 1 boson in the first box plus 1 in one of the 9 other states. So there are 9 ways to do that. Understand? I'm going to put 1 here, and then I have 9 choices for the second one. Now another possibility, let's leave the first one empty. Let's put 1 boson in the second box, and then how many ways do I have to put the second boson in the remaining boxes? 8, right? Plus 1 in the 8 other states. So there are 8 ways to do that. All right, then keep the first 2 empty and put a boson in box 3. And then put the second boson in one of the remaining ones. How many ways to do that? 7. You get the idea. You can go all the way down. 6, 5, 4, 3, 2, 1. Where by this 1, I mean that they are in the last, 1 in each of the last 2 states. With the first 8 before it all empty. Okay? Those are all the single occupancy microstates. You see what I'm saying? I'm just counting them up. So you add this column to get a total down there. Oop, question mark. How many are there that are single occupancy? Well, just add up the integers from 1 to 9. So that's a sum. We'll use an index I. We're adding up 1. Not 1. I, because we're adding up the integers. I goes from 1 to 9. 9, notice, is the number of states minus 1. Let me use the symbol n sub s for the number of states. So I'm doing that sum. Sum I going from 1 to n sub s minus 1 of I. That is n sub s times n sub s minus 1 over 2. That is 45. Okay? So there are 45 single occupancy states. Well, of course, there are 55 microstates total. So there are 10 more somewhere, yes? You see where they are? They're the double occupancy states, right? Because that's the other possibility with bosons. You have to keep track of what kind of particle you have if they're indistinguishable, and these are indistinguishable bosons. Bosons are perfectly fine having two or more particles in the same quantum state at the same time. So I also have to include double occupancy states. How many of those are there? Well, there are 10 boxes, i.e. 10 states, so there are 10 ways to do that. There are n sub s equal to 10 of these. Right? So, total number of microstates is 55. I'm going to label that omega sub b, the degeneracy for the case of bosons. That is that many singly occupied microstates plus that many doubly occupied microstates, which you can combine these and write it like this. N sub s times n sub s plus 1 all over 2, which is 55. Right? 10 times 11 over 2. 2 particles only, so the counting is simple. So the partition function for the case of bosons is the sum over all the microstates of the Boltzmann factor, but all the states have 0 energy, so once again, I'm just adding up the number of microstates. That means it must be the same thing as this degeneracy factor that I just calculated, right? So that's your 55. Now, like I said, this is a toy example with a small number of states and a small number of particles, just so that we can get practice with the counting. Okay? A real system would have large numbers of both states and counting. Okay? Notice, if you had a large number of states, that'd be the n sub s, this term is going to be considerably bigger than this one. There'll be a lot more singly occupied microstates than doubly occupied. All right, now that's bosons. What's the canonical partition function if the box contains 2 identical fermions? Okay, so now we have 2 identical fermions. So, how many microstates? How many ways to distribute the 2 fermions amongst the 10 boxes? So you might think of the picture basically like that, because they're indistinguishable objects, so you have your 2 dots again, but now the dots are fermions. So, how is the counting going to be affected now? Any thoughts?
We will not have any double occupancy.
You can't have the double occupancy. That's the only difference, right? So because they're fermions, no doubly occupied states. That's all. Can't have it. So the partition function z for fermions, sum over all the possible microstates, the Boltzmann factor for each microstate, which means just sum 1 over all the possible microstates. That's just going to end up being the degeneracy for the fermionic case. So what is that going to be? It's going to be 45, right? It's going to be n sub s, in this case, times n sub s minus 1 over 2, which which was the number of singly occupied states I had in my counting over there, which in this case is 45. Okay. So there are fewer states available to the fermions. Okay, all right. What is the canonical partition function for this system based on the quasi-classical system of indistinguishable particles? So now, okay, remember this is specific to a problem with 10 states and 2 particles. But I have 2 quasi-classical indistinguishable particles and 10 states. So ZQCL, quasi-classical. We learned in chapter 6 how to do the partition function for a multi-particle system of non-interacting, indistinguishable particles. You take the partition function for one of them, raise it to the power that is equal to the number of particles. I have 2 particles. Divided by the number of particles, factorial. Okay? Well, remember Z1, the single particle partition function, which is 10 in this case. 10 squared is 100, 2 factorial is 2, 100 divided by 2 is 50. The quasi-classical version of this problem would give a partition function of 50. Notice there's a bit of a pattern here. Okay. The pattern is for a given number of identical particles, and a given number of single particle states. The partition function for fermions is less than the partition function that you would have in the quasi-classical approach, which is less than the partition function for bosons. This has the fewest states because of the exclusion principle. Okay? This is the smallest of the 3 because of the exclusion principle, and the quasi-classical partition function ends up being right in the middle between the fermion and the boson partition functions. Okay. The difference ultimately between this and this is because of how double occupancy or multiple occupancy of the states is treated. Now, lastly, what is the probability of finding both particles in the same single particle state if they are identical bosons or if they are identical fermions? All right, I just did E, so now we'll do F. The probability for the boson case of double occupancy. Well, in this problem, it's just a number, it's a more counting. The number of doubly occupied states divided by the total number of possible states. How many are doubly occupied compared to how many total are there? Well, the number of doubly occupied states is equal to the number of those boxes I have up there. The number of single particle states, n sub s. And the total number of states possible is the degeneracy for the boson case. I've worked out that already in terms of the number of states. That's n sub s times the quantity n sub s plus 1 all over 2. So that, of course, simplifies to 2 over n sub s plus 1. Our n sub s is the number of single particle states, i.e. the number of boxes up there, which is 10. This is 2 over 11. What it simplifies down to, 2 over 11. And in the fermionic case, P sub f what's the probability of double occupancy? 0. Just write 0. No calculation there. 0. Okay. Okay, so this is a little bit of practice distinguishing between how bosons can distribute themselves amongst these single particle states versus how fermions can do it. And the difference comes down to how you deal with multiple occupancy of a given state. Okay, so now we're heading towards kind of the last big idea in this chapter. The rest of the chapter then being applications of this big idea. So let's set this up by first giving you kind of a roadmap for where we are right now. Okay? We're dealing with n-particle systems. Capital N is the number of particles. Okay? And we're assuming that they are of a single species. They're all the same, i.e. they are indistinguishable. Okay? First question. May we ignore the interparticle interactions? Are they interacting strongly with each other or weakly with each other? Okay? So that's the first question we'll ask ourselves. If the answer is no, we may not ignore interparticle interactions, then we are screwed. Okay? We have a hard problem. What do? Well, we start studying chapter 28 in this book, and then we go to graduate school. Okay? That's how you deal with a many-body interacting particle system.
You guys got this.
Okay? But if the answer is yes, say, okay, then we can use single particle states, like these boxes represented here. Right? Because that means you can solve Schrodinger's equation for one of those particles. Just find all the states available when there's one of them. And then you're just going to deal with those and putting your particles into them. Okay? You can do that if the particles don't interact with each other. Maybe we use semi-classical analysis. That's all depends upon how big the quantum volume is. Remember the condition for determining if you can do semi-classical or if you have to do fully quantum mechanical analysis. Look at how the quantum volume, its size, compared to the volume per particle. No, then it's fully quantum mechanical. Quantum statistics, this chapter. Semi-classical analysis, yes. Chapter 6. The partition function for the n-particle system is the partition function for one particle to the n power over n factorial. And then everything follows from the partition function. Okay? So we have done this route a lot now. And now we're heading down to go that way. Okay, so with that in mind, let me show you how we're going to do that last box. I'm going to introduce to you now two very, very famous results in quantum statistics. They are called, generically, distribution functions. So that's what I'm going to label. This is another section. Okay. So here's what we're going to do. First of all, slight change of perspective. In chapter 6, we took a system basically to be a particle. To get the Z1. Okay? To get the Z1, we took the system to be a particle. We took the reservoir to be all the other particles. Okay? We're going to change the perspective here a little bit. We're going to choose a system to be one single particle state. Like one of those boxes that I had in the example I just did. Not the particle that I'm going to put into the box, but the box, the state. Okay? One single particle state. And again, remember, by a single particle state, I mean a solution to Schrödinger's equation for a one particle system. It is, of course, as usual, specified by a set of quantum numbers. This single particle state. Specified by a set of quantum numbers. Okay? The reservoir is going to be all the other single particle states. So for example, if I had a so-called, well, if I had a box with impermeable walls, and any particle in this box could move around freely, but it cannot get out of the box, it can't get through the walls, then that's an easy problem to solve the Schrödinger equation for. It's called the infinite square well, or the particle in the box. Okay? And you discover, all right, so for the so-called particle in the box problem, that if you make a plot of energy, then you tend to draw something like this, where this represents the dimensions of the box. Okay? Then somewhere there's the lowest energy, obviously. Lowest single particle state energy. Somewhere down here there'll be like an epsilon 1. And then up a little bit will be another single particle state with energy epsilon 2. And they keep going. There are really actually an infinite number of them. So I'll pick another one up here, an arbitrary one, and it keeps going, dot, 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 upward. Okay? This is increasing energy going upward. This one is an arbitrary single particle state with energy epsilon. Okay? That's going to be our system. That state. I'm just picking one arbitrarily. Okay? Out of the infinite number of one states, single particle states that are available in this solution to Schrödinger's equation. Okay? So this represents the dimensions of the box going this way and just energy going up, and you've got discrete energy levels. Typical for a solution to Schrödinger's equation. I've picked one of the single particle states to call the system. Picked it arbitrarily. Okay? All right. Now, when this state is unoccupied, then we will say it's this system, I should say really when the system is unoccupied, its energy is going to be equal to 0. Energy of the system, I'll write those words, energy of the system equals 0. The state has a certain energy epsilon, but if it's not occupied by any particle, then that system has energy 0. Okay? All right, when that single particle level is occupied by little n particles, where that must be some integer, little n particles, then the energy of the system we will take to be little n times epsilon. Make sense? Okay? Please note this little n can be any integer, and it is not the same thing as a big N. Big N will be the total number of particles that are going to be put into these states. That's what we'll mean by big N, as we have always meant. Right? This little n is just any integer, depending upon how many particles are in this particular single particle state. Okay? All right. Now, we want to ask, what is the probability of the system being occupied by n particles? Little n particles. What is that probability? I'm going to label it P of n. Just going to be, because I'm using the grand canonical formalism, it's going to be the Gibbs factor over the grand partition function. Starting words with it. Okay? Because we're using the grand canonical formalism here. So it's going to be the Gibbs factor over the grand partition function. So in the numerator, the Gibbs factor is e to the negative beta times the energy of the system in the particular state, well, the state where I'm labeling it with this integer little n. Okay? So the energy will be little n times epsilon minus the chemical potential of the reservoir minus mu times the number of particles. Well, that's little n in this situation. So there's the Gibbs factor. Okay? And then I'll just use my standard symbol for the grand partition function for now, script z. So now let me just write this a little bit better by factoring in the numerator the integer little n out front. So minus beta times n times the difference epsilon minus mu all over the grand partition function. That's our first equation. Right there. Okay. Now we're going to have to figure out how to deal with determining what the chemical potential value is for this reservoir. And that actually turns out to be somewhat subtle. And we'll have to talk about that. But for now, this is the formalism. Okay? And what we're going to want to know is the average occupancy of each single particle state. On average, how many particles are in each state? You pick a state, you pick one of those, and I want to be able to calculate on average how many particles are in that state. That's where this is headed. Okay? Now the next thing we'll do is we're going to figure out what the grand partition function is. Because that's important, it goes there in the denominator. Of course, what that is depends upon whether the particles that I'm putting into these single particle states are fermions or bosons. Okay? All right, so we'll take our break, and when we come back, we're going to figure out, we'll have to do two partition functions, one for the fermion case and one for the boson case.